Hi everybody, welcome back to AP Physics with Mr. O'Hagan. Today we're going to be talking about conservation of momentum. Okay, I love this little discussion here we're going to have. Last year in intro physics, before we got to AP, when we did conservation of momentum, we did a couple like demos, and it just seemed like momentum was conserved, and it just seemed like a good idea. And then we made this incredible leap from, wow, it seems like momentum's to being conserved, to all of a sudden it was a law, the law of conservation of momentum. But there was no real justification for why it was a law. It was just Mr. O'Hagan told you it was a law, so it's a law. All right. But this year, we're going to actually give you the justification, show you how from this idea of center of mass and Newton's second law for a system of particles, conservation of momentum just flows naturally from it. Okay, so let's start off by recapping the things that we've got. So for center of momentum stuff, so conservation of momentum, for center of mass stuff, so the position center of mass of a system of particles would be x1, position 1, mass 1, plus x2, mass 2, position 2, mass of object 2, plus ... all divided by mass, and I will put the subscript down here, total, all divided by the total mass. All right, so that's center of mass, the position of center of mass with system of particles. Okay, so now then we differentiate this, and we get, for a system of particles, the velocity of the center of mass. And that would be the velocity of object 1 times the mass of object 1 plus velocity of object 2 times the mass of object 2 plus ... as many objects as you have, divided by the total mass. T-O-T, that stands for total. All right, and then we went one step further. We had the acceleration, center of mass acceleration for a system of particles, and guess what? Same exact format, and we just differentiated the velocity center of mass to get the acceleration. So we get acceleration of object 1 times the mass of object 1 plus the acceleration of object 2 times the mass of object 2 plus ... All right, and many of those you want to, all divided by the mass total, the total amount of mass. All right, so that's our center of mass equations. All right, position, velocity, and acceleration. Now we also had Newton's second law for a system of particles, and here was that. So the force net, so that's the force on all the objects, all of them, okay? All right, oops, I got my little note card here, I got it on the wrong side. All right, equals the total mass, T-O-T, times the acceleration center of mass. All right, that's Newton's second law, kind of the old-fashioned way if mass is constant. But we also had Newton's second law that looked this way. Force net equals d capital P. So this is the change in momentum divided by the change in time. First derivative of this idea of momentum. All right, and remember, momentum is just mass total times velocity center of mass. So that's the momentum of a system, remember, and it's capital P, and it comes from the momentum of an object, lowercase p, is the mass of the object times its velocity. Okay? All right, so anyway, so we've got 3 center of mass kind of equations. We've got Newton's second law 2 different ways. We have it the way Newton did it down here, talking about momentum, and now I've done momentum for a system of particles. All right, and that system of particles is the total mass of the system times the velocity center of mass of the system, okay? And then we have Newton's second law the old-fashioned way if mass is constant, okay? If mass doesn't change. All right, so these are our starting points. From these, we're going to be able to get conservation of momentum, and here's how we do it. All right, first step, let us assume a closed system. All right, if you remember, a closed system means there can be no forces from outside the system acting on particles inside the system. So for example, if I have 2 object system, All right, two object system. Okay, so here's mass 1, and over here is mass 2. That's supposed to be a 2, sorry. And let's say this is an enclosed system, or closed system, so I'll say closed, C-L-O-S-E-D-S-Y-S-T-E-M. All right, so the only forces acting on mass 1 and mass 2 come from mass 1 and mass 2. Nothing from outside the system, me outside the system, I can't reach in and go to mass 2, because I'm not part of the system. All right, so the only interactions we have is these two. So I will have, if they run into each other, I will have a force of mass 2 on mass 1, and then Newton's third law says, ooh, guess what? If you've got a force on mass 1 to the left of a certain amount, you're going to have a force on mass 2 to the right, because these are the ones interacting. And Newton's third law says, so this is going to be a force due to mass 1, that these two forces are equal in size and opposite in direction. Newton's third law. For every force on an object, there's an equal and opposite force on another object. For every force on mass 1, there's a force on mass 1, there's an equal and opposite force on mass 2. So, same numbers pointing the opposite directions. All right. Oh, these objects have mass. They're in the vicinity of each other. So there's going to be a force gravity possibly pulling them together. So this force is from them collision. These forces are from them being pulled together. And this force gravity is from object 2. And this force gravity is due to object 1. And guess what? For every force on an object, okay, so force gravity because of object 2 on object 1, it points to the right, has a certain size. There's going to be a force over here on object 2 pointing to the left, same size. Okay? So this is how a closed system works. It's easiest understood if you have two particles. But you can expand this same exact idea out to 3, 4, whatever particles you want. All right, so now here's the question. What is the net force, unbalanced force if you will, on a closed system? What's the net force on a closed system? I'll give you a second to ponder that. Okay. Any force you have on mass 1, there's going to be an equal and opposite force on mass 2. And they're always, for the system goes, going to cancel each other out. So for a closed system, remember, this is only going to be true for a closed system, force net is equal to 0. All right, and I'll write this in red. For a closed system, isolated system, everything we do from now on only applies to a closed system, an isolated system, okay? But if you have an isolated system, net force equals 0. Okay, got that idea. So where do we run with that idea? So there's kind of two different paths we can take on this one. Let's go and let's start with this idea. Okay, so we got force net is equal to 0. All right, and now let's look at net force kind of the old-fashioned mass is constant way. All right, going back to Newton's second law. So force net is equal to acceleration center of mass times the mass total. Okay? If the net force is 0, then, so since force net equals 0, comma, acceleration center of mass equals 0. All right. So for a closed system, the center of mass acceleration is 0, which means velocity center of mass is equal to a constant. Okay? That's an important deal. If velocity center of mass is equal to a constant, then we can say velocity center of mass initially, before something happens, equals velocity center of mass, the final value of it. Center mass velocity before equals center mass velocity afterwards. Ooh, we've got an equation. We know what velocity center of mass equals. Remember back here? Velocity center of mass. Velocity 1 mass 1 plus velocity 2 mass over mass total. Watch this. So I've got, remember it's a two-particle system. So I've got velocity 1 mass 1 plus velocity 2 mass 2. And I should say that, I don't like the way I wrote this. Let me write this again. Velocity 1 initial, mass 1, plus velocity 2 initial, mass 2, all divided by mass total, must equal velocity 1 final, mass 1, plus velocity 2 final, mass 2 all over mass total. Okay? So the idea here is now let's get that mouse out here. So this is the center of mass velocity kind of broken out into what it actually means before something happens. So initially, this is the center of mass velocity. Finally, okay, at the end. So I'm going to get rid of, I'm going to multiply both sides by mass total, and we get velocity of object 1, mass of object 1, plus velocity of object 2, mass of object 2, and I will say this is all initial before something happens, equals velocity of object 1, mass of object 1, plus velocity of object 2, mass of object 2, and this is all the final value of that. And guess what that looks like? That looks like a whole lot like conservation of momentum. All right? P1 plus P2 initial equals P1 plus P2 final. Conservation of momentum, stemming from Newton's second law and this idea of position of center of mass. Not so shabby. We now have conservation of momentum flowing from previously established laws. That's pretty cool. All right, so that's one way to do this, and we just started down this path using Newton's second law for an object where the mass doesn't change, for system particles where the mass doesn't change, okay? All right, yay, that works. We get to conservation of momentum. Here we go, conservation of momentum. All right, but now let's do it again because this is so cool. All right, so what did we start with? We said, hey, remember, force net equals 0. And of course, this is for a closed system, an isolated system. All right, once we have that, now let's go back to Newton's second law, but the way Newton actually intended it, the way he wrote it. Newton said the net force is equal to the first derivative of momentum, change in momentum over change in time. So d, and I'm going to use capital P, momentum of a system, divided by dt. All right? So if our net force is 0, since force net equals 0, comma, dp equals 0. All right? So there's no change in momentum. What that means is momentum of the system initial equals momentum of the system final. You want to expand this out to actual like numbers, to like letters. So momentum, now I'm going to lowercase. Momentum of object 1, let's do it this way. Momentum of object 1 plus momentum of object 2 equals momentum of object 1. Oh, poop, I screwed this up again. All right, here, let me start this again down here. Momentum of object 1 plus momentum of object 2 initially equals momentum of object 1 plus momentum of object 2, the final value. All right, you seeing conservation of momentum? Mass 1, velocity 1 plus mass 2, velocity 2 initial equals mass 1, velocity 1 plus mass 2, velocity 2 final. We're back to conservation of momentum. Here we go. Conservation of momentum. This is the law of conservation of momentum. Law, L-A-W, of conservation of momentum. Okay? And this law works only for a closed system. Law of conservation of momentum is only for a closed system. All right? A system where nothing else interacts. Nothing else interacts. All right, so how about this? How about this? Let me do this little question here. All right, remember, conservation of momentum usually works with collisions. Doesn't have to, but a lot of times we use conservation of momentum when things run into each other, okay? Or things start together and explode, okay? So anyway, how about this problem? I've got this car, velocity equals 0, and I got this car running in, okay, with some initial velocity. All right, these cars are going to crash. Okay, real situation. Real situation. Okay? None of this, ooh, laboratory, let's idealize it. Real situation. Car coming, car sitting still. All right, this is my wife, a couple years ago. She's sitting in our big giant van at a stoplight, and some, I don't know, some 20-year-old, 25-year-old plowed into the back of her. Okay? So now, if we use conservation momentum, here's what happens. All right, so let me come up with some numbers. Let's say this is 5. Let's say this is a mass of 10. Let's say this is a mass of 20. Okay, so conservation of momentum would do this. We would say, oh, and by the way, when they hit, they're going to stick together. Stick together. All right, because my van had a big giant trailer hitch on it that stuck out almost like, I don't know, about 9 inches, 8 inches, and this car actually impaled itself on this little trailer hitch. Okay, so let's say they stick together. So here we go. Law of conservation of momentum. Mass 1, velocity 1 plus mass 2, velocity 2. The initial value equals mass 1, velocity 1 plus mass 2, velocity 2. And this is the final value. Okay, the two ending velocities are going to be the same. All right, they're going to be the same. So here we go. Let's start plugging in numbers. So I've got mass 1's moving at 5. It's got a mass of 10 plus, oh, I wrote that wrong. I should put the mass first. 10 moving at 5 plus 20 moving at 0 equals, all right, so I'm going to pull out the masses. So I'm going to have, what's the total mass? 30 moving at some type of final velocity, because remember, they're going to stick together. Okay, so we get left side ends up being 50, the right side is 30, velocity final. So velocity final ends up being 50 divided by 30, 50 divided by 35, so 1.67. Yeah. All right. So it equals, yeah, 1.67. 1.67 meters per second. All right, so that's our combined velocity. All right, got it? Except in a real life situation, these things hit, boom, and the big van in front moves about, I don't know, 2 or 3 feet and stops. It just goes bonk and stops. It's not sailing off at this speed. It stops right away. Hardly any motion at all from that big van. Ugh. All right. In real life, velocity final is 0. What's going on? Like, what did we miss? Shouldn't this be predictive? It should. Except what's happening right now is, in real life, okay, we assumed a 2-particle system. And we applied conservation momentum on a 2-particle system, and we got this. which is what would happen if this was on this big, giant, frictionless plane, the slipperiest ice you've ever been on. That's what would happen. But it's not. It's on an actual street. And an actual street applies actual forces to the tires of the big, giant van. And those forces, once this collision happens, those forces go through the roof trying to keep this van from moving because the van has a lot of mass. So the reason why we only get a force, we get a final velocity of 0 in real life is, all right, not, okay, in real life, L-I-F-E, comma, system is not just two vehicles. Okay? All right? System is not closed. That's what happens in real life. If you want to know what really happens then, you got to include Earth in your system. Oh, what's Earth going to do? Earth is going to ever so slightly go, all right? But so insignificantly small because of the giant mass that you can't even measure it. But that's really what's going on. Okay? All right, so I showed you how to get conservation of momentum two ways, both stemming from real things, from real laws. So it's not just like, oh, it's a good idea, let's call it a law. It really is a law of conservation of momentum. And I've also shown you, be careful, it only applies to an isolated system. Now, don't get me wrong. You can get some really close answers assuming an isolated system. Because right after this thing collided, it probably went close to that number for a little bit before it stopped. But this only truly applies in an isolated system. Anytime you do it in real life, you're going to get super close numbers because you're going to have something that's super close to an isolated system. But it ain't. All right? So we can still use it to make predictions. But just remember, when our predictions are off from reality, the reason being is you don't have a closed system. And if you want to somehow get this to work out, add another object into your system. If that other object happens to be Earth, there's no way you can get it to work out. You just can't. You can't measure the velocity, final velocity of Earth to make this work out. Okay. All right, that is conservation of momentum. Oh, I also showed you a little bit of how you do a calculation with it. All right. I hope you enjoyed this. I really like this. That conservation of momentum now is really a law, and you can see really where it comes from. Okay, I hope you enjoyed it too. Adios for now. I'll see you around.